Welcome to this problem-solving session. Today, we're going to tackle an interesting problem from LeetCode, problem number 1198, find smallest common element in all rows. This problem challenges us to find an efficient solution by leveraging the sorted nature of each row in a matrix. Let's dive in and explore the different approaches to solve this. In this problem, we are asked to find the smallest common element in all rows of a given matrix. The matrix, referred to as mat, is structured such that each row is sorted in strictly increasing order. That means the numbers in each row are in ascending order without any duplicates. Our goal is to determine the smallest number that appears in every single row of the matrix. If no such number exists, the result should be -1. The input is provided as a list of lists, where each inner list represents a row of the matrix, and the output will be a single integer representing the smallest common element or -1 if there is none. Let's look at some examples to clarify this further. In the first example, the input matrix is provided as a list of 3 rows, 1, 2, 3, 4, 5, 2, 4, 5, 8, 10, and 4, 5, 8, 9, 11. Here, we need to identify the elements that are present in all 3 rows. By comparing the rows, we see that the numbers 4 and 5 appear in every row. Since we are tasked with finding the smallest common element, the result is 4. This is the smallest number that is common to all rows in the input matrix. In the second example, the input matrix consists of 3 rows, 1, 2, 3, 4, 5, 6, and 7, 8, 9. When we examine these rows, we find that there are no elements that appear across all of them. Each row contains completely distinct values with no overlap between the rows. As a result, there is no common element, and the output in this case is -1. Now for the third example. The input matrix contains 3 rows, 1, 2, 3, 4, 2, 3, 4, 5, and 3, 4, 5, 6. By comparing the rows, we observe that the numbers 3 and 4 are present in every row. Among these common elements, 3 is the smallest. Therefore, the output is 3. This demonstrates that even when multiple elements are shared across all rows, we only return the smallest one. Finally, let's review some important constraints and edge cases to consider. The matrix can be as large as 500 rows and 500 columns, meaning the algorithm must handle up to 250,000 elements efficiently. All values in the matrix fall within the range from 1 to 10 to the power of 4, and each row is sorted in strictly increasing order. For edge cases, think about scenarios like a matrix with only one row, where any element in that row is trivially common, or a matrix with no common elements, such as rows with completely distinct ranges. Additionally, ensure the algorithm can handle duplicate candidates across rows and verify its performance on the largest possible matrix size. These considerations are critical for designing a robust and efficient solution to the problem. To begin, let's consider the brute force approach. The intuition here is straightforward. Since each row in the matrix is sorted in strictly increasing order, we can focus on the first row and verify which elements are common across all other rows. The process involves looping through each element of the first row and checking its presence in every other row using a linear search. Once we find the smallest element that satisfies this condition, we return it as our result. However, this approach comes with significant drawbacks. The time complexity is O(m*(n), where we perform a linear check for each element in the first row across all rows. While this may work for smaller matrices, it becomes inefficient for larger ones due to the repetitive nature of the linear searches. Additionally, the space complexity is O(1), which is a positive aspect, but the time inefficiency makes this approach impractical for larger datasets. Now, we move to an optimized approach using hash maps. The intuition here leverages the row-wise sorted property of the matrix to track the frequency of elements across all rows. By using a hash map, we can count how many times each element appears as we traverse through the rows. At the end, we simply find the smallest element in the hash map that has a frequency equal to the number of rows, m. This element is our answer. The time complexity remains O(m*(n), as we still need to traverse the entire matrix, but it's more systematic compared to brute force. The space complexity, however, increases to O(n) due to the storage required for the hash map, especially in scenarios where all elements are unique. While this approach reduces redundant comparisons, the additional memory usage can be a limitation for larger matrices, making it less ideal in memory-constrained environments. Another optimization builds upon the sorted property of the matrix, using pointers to achieve greater efficiency. Here, we introduce an approach that avoids redundant checks by aligning pointers across rows. Starting with pointers at the beginning of each row, we identify the current maximum element among the elements pointed to. We then increment the pointers of rows where the current element is less than the maximum. This process continues until all pointers align at the same element, which would be the smallest common element, or until we reach the end of a row. The time complexity remains O(m*(n), since pointers may traverse their respective rows completely, but the space complexity is reduced to O(1), as we don't use any additional data structures. This method is particularly advantageous because it minimizes unnecessary comparisons and focuses on alignment, making it a more efficient solution overall. Given the options, the optimized approach using pointers stands out as the most efficient and scalable strategy for this problem. The main insight here is maximizing the utility of the matrix's sorted nature. Instead of repeatedly scanning rows like the brute force method or using additional memory as with the hash map approach, this method relies on aligning pointers efficiently. By incrementing pointers of rows with smaller elements, we eliminate redundant comparisons and avoid the overhead of extra storage. Key observations include the fact that the sorted property allows us to focus on the largest element in the current window across rows, incrementing only the necessary pointers to ensure alignment. While this approach has trade-offs, such as requiring multiple passes through the rows in the worst case, it significantly outperforms brute force in terms of speed and avoids the memory overhead of hash maps, making it the best choice for large inputs. The decision to choose the pointer-based approach is driven by its efficiency, scalability, and simplicity. By leveraging the sorted property, we minimize unnecessary operations and align elements systematically. Its O(1) space complexity ensures it scales effectively even with larger matrices, where memory usage can become a bottleneck. Additionally, the algorithm avoids the complexity of data structures like hash maps, making it easier to implement and understand. This balance between time and space efficiency makes it the most practical solution for the problem. It's clean, avoids redundancies, and is robust enough to handle diverse input sizes, which is why we ultimately selected this strategy. The problem we're tackling here is to find the smallest common element across all rows of a given matrix. Each row in this matrix is sorted in strictly increasing order, which gives us a structured way to approach the problem. The brute force method is based on a simple but effective intuition. By using the first row as our reference, we can iterate through its elements and check if each one exists in all the other rows. This minimizes redundant comparisons since the first row acts as a natural candidate filter. To start, we handle edge cases, such as empty matrices or rows. If the input is invalid, we immediately return an empty list. This ensures the algorithm doesn't proceed unnecessarily when the input doesn't meet the basic requirements. Once we've validated the input, the algorithm begins by selecting the first row as the reference. This is a key step because it significantly reduces the scope of our comparisons. We then iterate through each element of the first row, initializing a flag is_common to track whether the current element is present in all rows. For each element, we check its existence in the remaining rows using a linear search. If the element is missing from any row, we set is_common to false and skip further checks for that element. On the other hand, if the element is found in every row, we add it to the result list. At the end, the algorithm outputs this list of common elements. The reasoning behind using the first row as the reference is that it naturally narrows down potential candidates. If an element isn't in the first row, it can't possibly be common across all rows, so there's no point in checking it further. Additionally, since the rows are sorted in strictly increasing order, we can be confident there are no duplicates within a single row. This property simplifies the algorithm, as we don't need to account for repeated values. Addressing edge cases is also critical. For an empty matrix, we return an empty list since there are no elements to compare. If there's only one row, all its elements are automatically common, so we simply return the row itself. Finally, if no common elements exist across rows, the result will also be an empty list. To implement this approach, we rely on simple and efficient data structures. The first row is treated as the reference list, which we use to iterate over potential common elements. We then maintain a result list to collect the elements that are verified as common across all rows. Additionally, a Boolean flag _common helps us track whether a candidate element from the first row is found in every other row. These data structures are lightweight and straightforward, ensuring that the algorithm remains easy to understand and implement. When analyzing the time complexity of this approach, the dominant factor is the nested iteration. First, we iterate through the m elements of the first row, which takes m time. For each element, we perform a linear search across the n remaining rows, and if the average length of each row is k, this results in m*n*k in the worst case. However, there are scenarios where the algorithm terminates early, such as when the first element is not found in the second row. In such cases, the best case complexity is significantly reduced since we skip further checks for that element. This range between best and worst cases highlights how input characteristics influence performance. To improve the brute force approach, we can explore optimizations. One option is to replace the linear search with binary search. Since the rows are sorted, binary search reduces the time to check for an element's presence in a row from O(k) to O(log k). This change can significantly lower the overall complexity. Another optimization involves using hashing. By storing the frequency of elements across all rows in a hash map, we can quickly identify common elements without repeatedly scanning through rows. This method avoids duplicate comparisons and makes the algorithm more efficient, especially for larger matrices. This Python implementation solves the problem of finding the smallest common element in all rows of a sorted matrix. The approach utilizes a dictionary to track the occurrence of each element across rows and leverages the fact that the rows are sorted. 1. The smallest common element function is defined within the solution class. It accepts mat, a list of lists representing the matrix, as its input. 2. A dictionary element _count is initialized to store the count of each element encountered across all rows. 3. The variable rows is set to the total number of rows in the matrix. This helps us later determine if an element appears in all rows. 4. The algorithm iterates through each row of the matrix. For each number in the row, if the number is not already an element _count, it is added with an initial count of 1. If the number is already in the dictionary and its count is less than rows, to avoid overcounting duplicates within the same row, the count is incremented by 1. 5. After processing all rows, the dictionary contains the count of each number across rows. The numbers are then sorted in ascending order, and the algorithm checks if any number appears exactly rows times, indicating it is present in all rows. 6. The smallest number that meets this condition is returned as the result. If no such number is found, the function returns -1. This implementation is efficient for small to moderately sized matrices. Sorting the dictionary keys ensures that the smallest common element is checked first, adhering to the problem's requirements. In this implementation, we start by importing the necessary classes and defining our solution class. The method smallest common element takes a 2D matrix, where each row is sorted in non-decreasing order, and we aim to find the smallest element that is common across all rows. To achieve this, we utilize a hash map to count the occurrences of each element across all rows of the matrix. First, we determine the number of rows in the matrix and initialize the map. Then, we iterate through each row of the matrix. For each row, we use a hash set to track elements we've already counted within that specific row. This ensures we avoid incrementing the count multiple times for duplicate elements in the same row. For every unique element we encounter within a row, we update its count in the hash map using getOrDefault to handle cases where the element might not already exist in the map. This approach ensures that our count remains accurate and efficient. After populating the hash map with the occurrence counts, we need to identify the smallest element that appears in every row. To do this, we initialize a variable result with the maximum possible integer value. We then iterate through the entries in the map, checking if each element's count matches the total number of rows. If it does, we compare the element with the current result value and update result with the smaller of the two. Finally, we return the result. If no element is found that meets the condition, meaning result remains unchanged, we return -1 as specified in the problem requirements. This ensures that our method produces the correct output for all possible inputs. In this problem, we're tasked with finding the smallest integer that is common across all rows of a 2D matrix. The matrix is row-wise sorted in non-decreasing order, which is an important property we can leverage. If no such common element exists, we return -1. Let's start with an example to understand the problem more clearly. Consider the matrix mat, where each row is 1, 2, 3, 4, 5, 2, 3, 4, 5, 6, and 3, 4, 5, 6, 7. To solve this, the first step is to initialize an empty dictionary called element_count to keep track of how many rows each element appears in. We'll also initialize a variable rows and set it to 3, which is the number of rows in the matrix. As we process each row, we'll update element_count to reflect the frequency of elements across the rows. For the first row, 1, 2, 3, 4, 5, we start by iterating through it and updating the dictionary to include each element with an initial count of 1. After processing this row, element_count will look like this: 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Next, we move on to the second row, 2, 3, 4, 5, 6. For each element in this row, we check if it already exists in element_count. If it does, we increment its count, otherwise, we ignore it since we're only interested in elements that may appear in all rows. For 2, we increment its count to 2, and similarly for 3, 4, and 5. The updated element_count becomes 1, 1, 2, 2, 3, 2, 4, 2, 5, 2. Note that 6 does not exist in the dictionary, so we skip it because it can't be a common element. Finally, we process the third row, 3, 4, 5, 6, 7. Again, we increment the counts for elements that are already in element_count. For 3, 4, and 5, their counts increase to 3, while 6 and 7 are ignored. After processing all rows, the final state of element_count is 1, 1, 2, 2, 3, 3, 4, 3, 5, 3. At this point, we've captured how many rows each element from the matrix appears in. The next step is to identify the smallest element that appears in all rows. To find the smallest common element, we iterate through the keys of element_count in sorted order. This ensures that we'll encounter the smallest elements first. For each key, we check if its count equals the number of rows in the matrix, which is stored in the rows variable. If it does, that element is the smallest common element, and we return it. In this example, we start with 1 but find it only appears in one row, so we skip it. Similarly, 2 appears in 2 rows and is also skipped. When we reach 3, we see that it appears in all 3 rows. Since it's the smallest element that meets the criteria, we return 3 as the output. Now, let's consider another example to explore an edge case. If the matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, notice that no element is common across all rows. After processing all rows, the element_count dictionary will contain all elements but with a count of 1 for each. In this scenario, since no key has a count equal to the number of rows, we return -1 to indicate there is no common element. Finally, let's look at the case where the matrix has only one row, such as 1, 2, 3, 4, 5. Here, the solution is straightforward. We initialize the element_count dictionary and process the single row. Each element is added to the dictionary with a count of 1. Since there is only one row, every element in this row is considered common, and the smallest element is simply the first element in the row. Therefore, the output is 1. This example highlights that when there is only a single row, the solution reduces to returning the smallest element of that row, as there are no other rows to compare with. These examples demonstrate how the solution utilizes the properties of row-wise sorting and frequency counting to efficiently determine the smallest common element across all rows of the matrix. To analyze the time complexity of this solution, let's first break it into its main components. The code begins by iterating over each row of the matrix. If the matrix has m rows, this iteration contributes O(m) to the overall complexity. Next, within each row, the code processes all elements, and if there are n columns, this inner loop contributes O(n) per row. Together, these nested loops result in O(m*n) iterations, as every element in the matrix is processed once. Additionally, for each element, the solution performs dictionary operations such as checking for existence and updating counts. These operations have an average time complexity of O(1) due to the use of Python's hash tables. Since there are m*n elements in the matrix, dictionary operations contribute another O(m*n) in total. These steps form the core of the solution's time complexity. After processing the rows, the solution sorts the keys of the dictionary. If the matrix contains k unique elements, sorting these keys takes k*log k. For matrices with a relatively small range of integers, sorting might not dominate the runtime. However, in cases where the range of elements is large, this sorting step can become significant. When combining these steps, we get the overall time complexity. In the worst case, this is determined by the nested loops in the sorting step, giving us O(m*n plus k*log k. If the number of unique elements k is proportional to the total number of elements m*n, the time complexity simplifies to O(m*n*log m*n in the worst case. This provides a comprehensive view of the time complexity under different scenarios. Now, let's examine the space complexity of the solution. The key contributor to additional space usage is the dictionary, which stores counts for all unique elements in the matrix. If there are k unique elements, the dictionary requires k space. Sorting the dictionary keys also requires temporary space, which is another k. The input matrix itself takes O(m*n space, but since it is part of the input, we do not count this as additional space. When we combine these factors, the overall space complexity is k, where k is the number of unique elements. In the worst case, where all elements in the matrix are distinct, k could be proportional to m*n, making the space complexity O(m*n). To put this into perspective, let's compare the current solution to a naive approach. In a naive method, we would iterate through all possible integers in the range of the matrix and count their occurrences row by row. For each integer, checking its presence in all rows would take O(m*n, and this would be repeated for every number in the range. As a result, the time complexity would be O(range*m*n, where range is the maximum possible element value. On the other hand, the optimized approach avoids this inefficiency by using a dictionary to track counts in a single pass. This eliminates the dependency on the range of elements and achieves a time complexity of O(m*n plus k*log k, which is far more efficient when the range is large. Regardless of the case, whether best, average, or worst, the optimized solution processes all elements and sorts the dictionary, so its worst-case complexity remains O(m*n plus k*log k. Finally, let's verify the big O analysis. The nested loops ensure that every element in the matrix, exactly m*n elements, is processed once, contributing O(m*n to the time complexity. Sorting the k unique elements in the dictionary adds k*log k. When we combine these two, the total time complexity becomes O(m*n plus k*log k. This is a tight bound and accurately represents the worst-case scenario, as it accounts for all the operations performed by the solution. Thus, the analysis confirms that the solution consistently adheres to this upper bound, regardless of the input. When solving this problem, there are a few common mistakes to watch out for. First, many solutions fail to take advantage of the fact that each row in the matrix is sorted. Ignoring this property often leads to inefficient brute force solutions. Instead, you can use binary search or merge-like techniques to leverage the sorting and optimize your approach. Another mistake is not handling duplicate elements properly within rows. For example, if rows contain duplicates, naive approaches might overcount these elements, leading to incorrect results. A better solution is to use a hash map or frequency counter to track unique elements. Additionally, you should avoid assuming that all rows have the same length. While it's common to see uniform row lengths in problems, this assumption can lead to index out-of-range errors. To handle this, always validate the input and dynamically account for varying row sizes. Lastly, repeatedly iterating through all rows in a brute force manner can result in a time complexity of O(n²*m, which is highly inefficient. Instead, you can use a hash map to avoid redundant checks, or even employ a priority queue to efficiently find common elements across rows. Another important optimization opportunity is to recognize early termination possibilities. If one of the rows does not contain a particular element, there's no need to continue checking the other rows. Naive approaches might miss this and keep iterating unnecessarily, wasting computation time. By exiting early when a mismatch is found, you can save a significant amount of processing effort. Now, let's consider the insights that can help during interviews. Many matrix problems rely on leveraging the sorted properties of the data, whether that's row-wise, column-wise, or both. Recognizing these patterns is key to crafting efficient solutions. When comparing hash map-based solutions to pointer-based ones, hash maps are often more intuitive for counting frequencies across rows. However, pointer-based solutions, such as those using K-way merge techniques, are typically more space-efficient and preferred in interviews. It's also crucial to clarify constraints with the interviewer, such as whether rows can be empty, contain duplicates, or vary in length. This demonstrates your thoroughness and attention to detail. Lastly, discussing the trade-offs between brute force methods with O and squared *m, complexity and optimized approaches with O and *m log m, or better will show your understanding of scalability and efficiency. This problem also shares similarities with several related matrix-based problems. For example, LeetCode 378, kth smallest element in a sorted matrix, LeetCode 240, search a 2D matrix 2, and LeetCode 74, search a 2D matrix, all challenge you to make the most of sorted data structures. Additionally, LeetCode 23, merge k-sorted lists, provides a similar opportunity to practice k-way merge techniques. Now, let's explore some alternative approaches to solving this problem. The hash map approach involves counting the frequency of each element across rows. This method has a time and space complexity of O and *m and is relatively simple to implement. However, it does require additional memory for the hash map. Another option is the pointer-based row intersection technique. Here, each row is treated as a sorted list, and you use a k-way merge technique to find the intersection. This approach has a complexity of O and *m log m when utilizing a priority queue. While it's more space efficient than the hash map method, it can be slightly harder to implement, so it requires careful attention to detail. One more alternative approach to consider is using binary search on each row. In this method, you iterate through each element in the first row and use binary search to determine whether that element exists in the other rows. This takes advantage of the sorted nature of the matrix, resulting in a time complexity of O m *n log n. While this approach can be effective for smaller matrices, it may become slower for larger ones compared to the pointer-based method. Ultimately, the choice of approach depends on the specific constraints of the problem, such as the size of the matrix and the available memory, as well as your familiarity with each technique. Understanding these trade-offs will help you tailor your solution to the scenario and demonstrate your problem-solving skills effectively. Great job! To summarize, we explored various approaches to solve this problem, leveraging the sorted matrix property for efficiency. Remember the importance of analyzing trade-offs between time and space in problem solving. Thanks for watching, and be sure to practice similar problems to strengthen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!